Hi guys, welcome to yet another video on motion, and in this video we are going to talk about non-uniform motion. So last video we talked about uniform motion, which was one of the simplest kind of motion, that is a body moving with constant speed, right? You might argue that rest is the simplest kind of motion, isn't it? But I would counter argue and say that it doesn't make a difference, because a body moving with constant velocity is same as a body at rest. Motion is always relative. So whenever we are saying it's moving with some velocity, there is a hidden thing that our observer is on the ground and he's at rest. So that simple thing was the thing of the past. Now we'll add a little twist in the motion. So previously we saw a body moving with constant velocity, let's say 5 meter per second, that is it was doing equal distances in equal intervals of time. Now what we'll see is unequal distances in equal intervals of time. So let's say there's a body which is in first second it does 5 meters, but in next second it does 7 meters, in next second it does 10 meters. So this is the motion which we are talking about in this lecture. So that will be non-uniform motion. But as we have divided motion into two parts, uniform and non-uniform motion, on the basis of whether the displacement is increasing or decreasing uniformly with time or non-uniformly with time, and in the same way we'll divide non-uniform motion into two parts, that is uniformly accelerated motion and non-uniformly accelerated motion, on the basis of whether velocity is increasing or decreasing uniformly with time or non-uniformly with time. So the purpose of this video will be to see uniformly accelerated motion, and one of the best example of uniformly accelerated motion is the motion of a body which is free falling under gravity. But this was not a common information before Galileo. Galileo informed us that the motion of a free falling body is a uniformly accelerated one. Galileo actually taught us two things about motion of a body under gravity. The first thing was that the motion of a body under gravity is not dependent on its mass. It's independent of how heavy the body seems to be. That is, if you take 1 kg ball and a 10 kg ball and you drop them from the same height, then both will reach the ground at exactly the same time. The second thing he told us was that acceleration is constant. Near the surface of the earth, you can take this acceleration to be constant, and he did not only told us that, he actually gave us the value of that acceleration. He told us that acceleration due to gravity, which will symbolize as a special symbol g, is 9.8 meters per second square. And what does that mean is, if you drop a ball from some height h to the ground, it will start with speed 0, but if you measure its speed after 1 second, its speed will be 9.8 meter per second. 1 second more later, its speed will be 18.6 meter per second. That is, the increase in speed every second is 9.8 meter per second. And that essentially means that acceleration of the body is constant and is 9.8 meter per second square. So for all of the problems that you'll do in mechanics, you have to take acceleration due to gravity as constant, and it's equal to 9.8 meter per second squared. So how does it feel? Does it even feel to be in accelerated motion? Because we see that whenever we move with constant velocity, we don't actually feel the motion. Let's say the train is running smoothly on a track with constant velocity in one particular direction, you wouldn't feel that train is even moving or not. It's the same case with bus. But when it starts to accelerate, or when it slows down, when it brakes, then you feel that there is some kind of force acting on you that is pushing you forward or backward, or whenever it tries to turn, you'll feel a force in the opposite direction of the turn. So what I'm trying to convey to you is basically reinforcement that motion is relative. All the rest and uniform motion are the same thing. That is, if you are moving with constant velocity, v equals constant, then it's actually equal to being at rest. You wouldn't feel. All the laws of physics will eventually work the same. If you keep a football on the table, let's say, which is on the train in front of you, then nothing would happen to it if the train is moving smoothly with constant velocity. But once it starts to accelerate, then you see the laws of physics are acting weirder. The football will start to run backward. So when v is constant, you don't feel anything. But once it starts to accelerate, acceleration is there, you can say acceleration is not 0, then you will feel the motion, you will feel there's a kind of force acting on you. But all of that we'll discuss in the dynamic part of the motion. Let's first be clear about what are all the conventions that we are going to use. So you know the conventions that are there in the graphs. Right is positive, up is positive, left is negative, and down is negative. That is, I have to put a number. I'll put positive numbers in this side, positive numbers here, but negative numbers here and negative numbers here. So for you the problem is quite simple, as you have to only study motion in 1D. So it will be either along x-axis or motion will be along y-axis. It could also be along some particular axis like this. So you can ask, sir, what would happen if this is the question, where would I take positive or where would I take negative? So if that is the case, you can take anything, because conventions are just there such that everyone uses the same thing. It's not a strict rule that you have to use that. So you can build your convention and you say that, yeah, this I'll take as positive, this I'll take as negative, but you have to be strict towards it. You always have to use this as the convention. So as I told you, you can take your motion to be along a number line, that is 0, 1, 2, 3, -1, -2, and object would be moving along this number line, where these numbers represent position of the object. So if an object, let's say it goes from -1 to 3, obviously it will not go in this path, it will go in a straight line. This is just to show it's going from 1 to 3. So if that is the case, if I had to find displacement, I'll say displacement is nothing but delta x, that is x final minus x initial, which would be 3 minus of -1, which is 4. So displacement comes out to be 4. What if it was the opposite case? What if it was something like -2 to 0? And you know that it's going like this. So in that case, if I calculate the displacement, that would come out to be xf minus xi. Xf would be 0, minus xi is 2. It comes out to be -2. What does that minus represent? This minus represents the direction. So displacement was towards left. It is +4. That means displacement was from -1 and how much? 4 towards the right hand side. And as velocity is equals to displacement over time, velocity would also be positive if something is moving towards right, and velocity would be negative if something is moving towards left. But same things cannot be said about acceleration. As velocity is simply x over t, you'll see in vector chapter what do I mean by these vector signs. As velocity is a vector which is equals to one vector over scalar, both of their directions are equal. But if I had to write acceleration vector, it would be v vector minus u vector over t vector. So it's not simply the direction of v vector or u vector, it's subtraction of v vector and u vector, which we don't know where it will go. So how to decide? So we'll decide on the basis of change in velocity, right? Because our question is pretty simple, we don't have to use these vector formats, it will be just positive or negative. So let's say I have thrown a ball in upward direction, right? So its velocity is 30. Now let's take acceleration due to gravity to be 10 meter per second square. So after 1 second, if I ask you what would be its velocity, so as it is 10 meter per second square, I've told you it would be 10 meter per second per second. So velocity is changing by 10 meter per second per second. So after 1 second, its velocity, would it be 40 or would it be 20? It would be 20, right? Because acceleration which this guy is facing is equals to minus g, minus 10 meter per second square. So after 1 second, its velocity would be 20. After one more second, its velocity would be 10. Then finally, at this point, it will be 0, right? So how did we decide the direction? How did we decide the sign of acceleration? It would decided on the basis of whether the velocity is increasing or decreasing. So acceleration is positive if velocity increases, and acceleration is negative when velocity decreases. So here you can see velocity is decreasing, 30 to 20 to 10 and to 0. And you might have heard that we take acceleration due to gravity always as -10. And why is that? Because of the same convention which we talked about just now. After 0, it will be moving with speed 10, but that speed 10 is in negative direction. So its velocity essentially here is minus 10. So you could say that from 0 velocity it decreased to minus 10. So that's why we take acceleration while going up, while going down, both as negative 10 or 9.8 meter per second square. Okay, so we have seen a little bit of graphs, but not so much. So let's try to make some graphs. So let's say I have this x-axis as displacement and this axis is time. And there's one guy which is moving with 2 meters per second. So it's starting from position, let's say 0, and it's moving with 2 meter per second. So first thing what you do is you make some tables, that at this time this was displacement. So at this time this was 0, at 1 time it would be 2, at 2 times it would be 4, at 3 times it would be 6, and so on. How do you make a graph? You plot those points: 0, then 2, then 4, then 6, then 8, and then finally you join those dots to get a curve. But what if it was a different curve? So if it was a different curve, let's say it was a velocity time graph, then you had to make points for velocity, that at t equals to 0 velocity was 2, at t equals to 1 velocity was 2, 2 also 2, and 3 also 2, dot dot dot. So how do you make a graph? Exactly the same process. Plot the points, plot the points, plot the points, plot the points, and join them. So it will come out to be a straight line graph. What if it was acceleration time graph? So if it was acceleration time graph, it would be a t, then you would make a curve for a again. So at t equals to 0, acceleration was 0, 0, 0, 0, dot 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 dot. Why? Because velocity is not changing. So how would the graph look like? Graph would look like this straight line on the x-axis. Now let's try to make a graph for uniformly accelerated motion, that is a body changing its velocity constantly at constant rate. So here is our body. Let's say it starts from position equals to 0 with initial velocity equals to 0, but it has some acceleration equals to 2 meter per second square. Now it will move in this direction like this, and we have recorded some data for it, that is t equals to 0, x was 0, velocity was 0, but acceleration was 2. At t equals to 1, as acceleration is still 2, velocity would be increased by 2 meter per second, and displacement came out to be 1 meter. So that's how we have recorded the data. So let's start with the easiest graph. So the easiest graph would be acceleration versus time graph. What to do? Plot the points. This is 2 over here. So 2, 2, 2, 2, 2, 2, 2, straight line. That means acceleration is constant. Let's try to make another graph. So the another graph would be velocity time graph. How do you think it would look like? Velocity starts from t equals to 0, 0. Then at t equals to 1, velocity is 2. So this point right over here. And t equals to 2, velocity is 4. This point and this point. It will come out to be a straight line like this. Let's try to make displacement time graph. So we'll do exact same thing, plot the points, then join them. So at t equals to 0, displacement is obviously 0. T equals to 1, displacement is 1. Then at t equals to 2, displacement suddenly climbs up to 4. Then t equals to 3, displacement is 9, which is out of the picture. So it will come out to be something like this, like a curve. And if you might ask, why is it not a straight line? The answer is pretty simple. It's not a straight line because a graph is only a straight line when y-axis increases or decreases uniformly with x-axis. And here, position or displacement is not increasing uniformly with time, so it will not be a straight line. So finally, we have reached to the fun part. We did all of the work behind it just to reach here. So we started off by defining quantities, that this will be displacement, this will be distance, this will be acceleration. Then we tried to measure some quantities, we tried to form some data sets, then we tried to make sense out of data sets by plotting graphs of it, and then finally we found out some laws of the nature. So these are some laws of the nature. These are called equations of motion. So you can see here 5 equations of motion, 5 gibberish of some letters. We'll talk about what all of them exactly means. But before starting equations of motion, let me tell you that in most of the books you'll see this as the first equation of motion, this as the second equation of motion, and this as the third equation of motion. Alright, so let's start. So here we have a body's initial position, here we have body's final position. Let's define some parameters. It starts with initial velocity u, it has a final velocity v, it did that change of velocity with constant acceleration a. The change happened over a period of time t, and it did some s displacement in that time. Now let's derive some equations. So first equation actually comes from definition of acceleration, that acceleration is v minus u over t. So this equation can also be used to calculate the final velocity, which will be equal to u plus at. So this equation simply says that give me time, I'll give you the velocity. First thing would be that if acceleration is equals to 0, then v would be equal to u. Final velocity would be equal to initial velocity. There would be no change in velocity. But if it is moving with some constant acceleration a, then its final velocity v will be equal to u plus a after 1 second, or it will be u plus 2a after 2 seconds. So after t seconds, it will be equal to u plus a into t. Now if you remember the velocity time graph in uniformly accelerated motion, it was something like this. So velocity is increasing uniformly from u to v. If uniform is increased, then you can say that velocity average is equals to v plus u by 2. And if this is the average velocity by which it is moving, then we can simply say that displacement done in time t would be equals to v plus u over 2 into t. Now displacement in accelerated motion comes out to be v plus u over 2 into t, and we also know that v can be substituted as u plus at. So this equation becomes something like this, and this is nothing but ut plus half at squared. So this equation simply says that displacement is a function of time, or if function is a hard word for you, you can simply say displacement is dependent on time. So if v is equals to u plus at, that gives me time must be equal to v minus u over a. And if displacement is ut plus half at square, and I don't want this equation in terms of time, then I can replace time from the first equation as v minus u over a. And if I do that, it would become u into v minus u over a plus half into a into v square plus u square minus 2uv over a square. So that would give me uv minus u square plus a gets cancelled, so divided by 2a, and this is only divided by a, and this will be v square plus u square minus 2uv, and if you add them together, 2uv, and if you add them together, 2uv and 2uv will get cancelled, and you'll get v square minus u square over 2a, which simply gives you your this equation that v square is equals to u square plus 2s. And finally, taking the second equation, s equals ut plus half at square, and replacing u as v minus at, so v minus at into t plus half at square will give me vt minus at square plus half at square. So this gives me my final equation, s equals vt minus half at square. Alright, so we have seen how to prove all of the equation, but proof is not important. What important is that what actually these equations are saying. So don't get frightened by all of those equations. You just need mainly two equations, this equation and this equation. So this equation you already knew that final velocity can be found out as u plus at, and this is the new equation which you are getting is s will be equal to ut plus half at square. So remember these two and you'll be good. Alright, so finally, how to solve problems, that is the major part, right? Because most of us generally don't like physics because problems are too tough, or we couldn't understand the problem, or I couldn't get physics because my math is weak. So there are many reasons. So we have to not just be theoretical about it, we have to also solve some problems. So let's imagine a scenario with this car right over here starts from position xi and it has some initial velocity which will say v naught or it's equals to u. After some time this car will have some velocity v, so its position will be xf. Now it did that with constant acceleration a and it took time t and displacement was s. So as you can see here, you're juggling with majorly 5 quantities. What are they? S, u, v, a and t. And if you see all of the equation that we have seen before, all the equation, you would see that in all of the equation there are 4 variables. 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. So that's why we got 5 equations, because we had 5 variables and in all of them there are 4 variables. That is, in each of them there is one variable that is not there. That is, in this equation you wouldn't see s is not there, this a is not there, in this v is not there, in this t is not there, and in this u is not there. Hence what you need to do is pretty simple. First you need to write all the things that are given in the question, that we call as givens. Now what you have to do with givens is write them with convention, that is, write them with sign. If velocity is towards left, write it as negative. If velocity is positive, then write it as positive. If it's going down, then take displacement to be negative. Acceleration due to gravity, you already know you have to take it as a minus 9.8 or minus 10 meter per second square, irrespective of whether the body is going up or down. And once you write all the given variables, you would realize that in each of the question you are given 3 given variables. And that's pretty obvious, isn't it? That if all of the equation contains 4 variables, then you couldn't solve with 2 variables because 2 will be unknown. So that will be unsolvable. So problem setter will give you 3 variables and they'll ask you other 2 variables which you could find from any of the equation that you would like to apply. Now to get more familiar with uniformly accelerated motion, let's solve some problems on that. Alright, so first problem is a body starting from rest moves with a constant acceleration for 20 seconds. So it travels for a total of 20 seconds. Now it travels a distance of s1 for first 10 and s2 for final 10. Find s1 over s2. So let's say this is s1 and this is s2. Here also time equals 10 seconds and here also time equals 10 seconds. Can we say s1 equals to s2? That we know is obviously not true, because it's an accelerated motion where unequal distances and equal intervals of time. Let's also write its initial velocity as u. Let's say here the velocity was v1, here the velocity is v2. Now let's start writing the equation. So first of all we can say v1 must be equal to u, which is equals to 0 because it's given that it starts from rest. So 0 plus a into t, so a into 10. So v1 is nothing but 10a. How about v2? v2 is same u plus at, u is equals to 0 plus a into 20 seconds. So that would be equal to 20a. How about s1? s1 could be written as ut plus half at square. U is 0, so it's 0 plus half into a, time is 10 squared. So s1 comes out to be 50a. How about s2? s2 is v1t because it starts with v1 plus half at square. So this would be v1 is how much? 10a. So 10a and t is already 10 seconds plus half into a into 100, that is 10 squared. So this comes out to be 150a. So that gives us our answer. S1 over S2 equals 50a over 150a. That will be equal to 1 over 3. You could also have given the answer directly, because you know that s equals half at square when u is equals to 0, like in this case. That is, s is proportional to t square because half a is constant. So what it travels in 1 second will be 1/4 of what it travels in 2 seconds. So this thing must be 1/4 of this thing. What does that essentially means? That this is 1 and this would be 3. Let's start with problem number 2. So this says a student is standing 50 meters in front of the bus. As soon as the bus begins its motion with an acceleration of 1 meter per second square, the student starts running towards the bus with a uniform velocity v. Find the minimum value of v for which he'll be able to catch the bus. So this is the scenario. So here's the bus. So let's say this is the bus, and here is our student, which is running there with constant velocity v. What's happening to the bus? The bus starting from rest and it's accelerating with 1 meter per second square, and we have to find that if initial distance between them was 50 meter, what should be the minimum velocity v such that he'll be able to catch the bus. So whenever this type of problem comes, you know what to do. Take a final case. So let's say they meet at this point here. This distance is equals to x, and let's say it took time t. So after time t, the bus also should be here and the person should also be there. Now let's write the equation. So the first equation would be that v into some time t must be equal to 50 plus x, as the boy is moving with constant velocity for time t and is traveling a distance 50 plus x. Now for the bus, we can say that x is the amount he travels, but it is an accelerated motion, so we have to use ut plus half at square. U is 0, so it's just half at square, so half into a is also equal to 1 into t square. So this simply gives us x equals t square over 2. So that is our equation number 2. This was equation number 1. But here's the problem. We have 3 quantities v, t and x, but only 2 equations. How can it be? Did we miss something? Yes, indeed we did. Because he's asking minimum value of v. Just imagine if we travel at half the speed of light. Won't we be able to catch the bus? Obviously we'll be. So what's the major point of this problem? He's asking minimum possible value of v you can manage and still catch the bus. That this tells me that if at the point of the meeting, if bus travels with more velocity than the boy, then boy will not be able to catch the bus, because bus is accelerating. He'll continue to increase its velocity, but boy will not be able to. Hence we got our third equation, that is final velocity of the bus must be equal to final velocity of the boy, which is same as the initial velocity of the boy. So let's say bus's final velocity was v1, so v1 was equal to initial velocity of the bus, which is 0, into acceleration, that is 1 into t, and that must be equal to velocity of the boy. So this gives us our third equation, that v is equals to t. Now let's try to solve it. So v into t equals 50 plus x, x equals t square by 2, and v equals to t, that is my third equation. So what do we need to find? We need to find v. So let's replace t as v. So here I can see t, so this will become v square equals 50 plus x. That is the first equation, right? Here x equals t square over 2. So v square equals 50 plus t square over 2, and t is also equal to v, so v square equals 50 plus v square over 2. That gives us v equals to 10 meters per second. Alright, so finally, what is the whole takeaway of this video? So the first thing we learned is that motion can be uniform and non-uniform, that is if it's moving with same speed or variable speed. When it's traveling with variable speed, there is a quantity that comes into the picture that will be called as acceleration, and that is equals to change in velocity over time. So when we are talking about accelerated motion, we are talking about a motion in which the body is changing its speed constantly. Now it can change its speed constantly with a uniform rate or with a non-uniform rate, or randomly also. So in all of those cases, we have divided into two parts: motion with uniform acceleration and motion with non-uniform acceleration. So when it's motion with uniform acceleration, speed changes at a constant rate, and that is the motion which we talked about in this video. The second thing we learned is how to make graphs and follow the conventions, that right and top will be taken as positive, left and bottom will taken as negative. That is true for displacement and velocity, but you cannot say for acceleration. Displacement, when it's in right direction, is positive, left is negative, up is positive, down is negative. Same thing with velocity. If it is upwards positive, right is positive, left is negative, and bottom is negative velocity. But sign of acceleration depends on the change in velocity. So if velocity is increasing, then it's positive. If it is decreasing, then it's negative. Always remember, it's increase in velocity. third thing we discussed was the equations of motion and how to solve it. So we saw there are mainly three equations of motion: v equals u plus at, s equals ut plus half at square, and v square equals u square plus 2s. And we also saw how to use these equations.